Greetings and welcome, Mr. Waddy. We're talking about congruence and transformations. It says the following: two geometric figures are congruent if and only if. Oh, biconditional statement. That means it's true both ways. If there is a rigid motion or composition of rigid motions that maps one of the figures onto the other. Congruent figures have the same size and shape. I like this explanation a lot. That's not like the official definition, but that's like a good way to think about congruence. Same size and shape versus these are the same shape but different sizes. And right, these are just different shapes. Those are, yes, they're both triangles, I understand, but they're not like the same triangle. They have different ratios of sides and they have different angle measures. So that's the idea of congruence. Actually, I was in a conversation with a math department teacher the other day about Common Core's use of the definition of congruent and it linking that definition specifically to the idea of transformations. That even if I was to talk about congruent angles, that there should be a transformation that maps one angle exactly onto the other. All right, and that's actually a way to define congruent. And similarly for segments, if I'm talking about congruent segments, all right, let's say that these two segments are congruent, that there should be some transformation or series of transformations that would map one of the figures into the t'other. And map them onto each other, and that's actually a way that you can define congruent, and Common Core apparently loves it. So here we go, congruent, not congruent. The layman's definition for congruent could be same size and shape when it comes to the figures. All right, ooh, identifying congruent figures. All right, so What do you guys think? You notice any figures that are congruent? How about I call this one ABCD. Looks like a square. Man, how do I? Yeah, I guess I'll put the square shape over there. I'm gonna say is congruent to square. I guess I could actually start in any order for these letters, but I'll just call it NRQP. I don't know, I just made it up. I know that I've seen the symbol for parallelogram before, but either way, whether you think I'm talking about a quadrilateral, it doesn't matter. Those two things are congruent to each other. Thank you, thank you. So what would your explanation be to justify their congruence? Is there a transformation that you could describe that would bring one onto the other? It looks like if I mapped it by vector what now? -2, -6, that it would map one of those figures onto the other. Therefore, they are congruent. By the definition of congruent figures. Excellent, excellent. All right, how about this one here? Ooh, does it have a congruent, buddy? Triangle feg is congruent to triangle who? Nope, I disagree. I think this one's slightly muggles can't use magic from what I understand. But also, this is actually a new experience for us regarding congruent figures. Even though you're referring to the same triangle, we'll try to name the congruent figures so that their corresponding parts line up in their names. So the F is going to be corresponding to the L. So when I name that triangle, yeah, lookum. Yes, about chicken names. Yeah, it's like you didn't even know par or ghost. So what's a transformation that would have mapped those triangles onto each other? Reflect over what? over, I think, just the x, right? If I mirror it just over this, this distance and this distance are congruent and perpendicular, and this one to this one. Yeah, you get the idea. But as far as naming these, the sequence of the name matters, similar to how we did the other things. Let's see. Let's pick up the pace, Waddy. All right. This guy. I'm gonna call this Triangle. Hi, Jay. I've got a brother named Jay. He's my older brother. Hi, Jay. This video's just shout out to Jay Waddy. Represent. No, I make 21 videos a week. Like, no one that cares about me watches them. Oh man, that was like a little, that was just a little bit too real right there, friends. I'm sorry. Okay. It's like I'm trying. You guys know I do the shout outs to my friends and family all the time, and I've never gotten a response. It's like they don't even care about my internet fame. Also, happy birthday to my middle son, Griffin, today. 3/13/2017, 4 years old. Woo! We got him some Legos. Yeah. Oh, my kids are Lego master builders at a very young age. I'm training them. Actually, this is just all on the internet, yes. And actually, I was like a little sad the other day. And my son Everett was like, "Dad, you're the best Lego builder." And I was just like, this was the most important thing that's ever happened to me. My son realized my Lego building skills because I destroy him at Lego building every day. And just to show him who's boss. Like, you can't outdo your dad. Like, knock his Legos down. Yeah, classic dad. Yes. So anyways, what triangle, hi Jay, is congruent to hi Jay? Anybody help me out here? Well, I started at H. Sut. You actually, because this triangle would have a symmetry, you actually could have started at U or S. I'm gonna start with S, I think. And Stu. Yeah. I don't know anyone named Stu, but if maybe Stu was like one of my backers on like GoFundMe for the Waddy Math channel, and this is like his special, like he went over the top $100 donation, like he gets a shout out in a triangle named after him. Man, I really should do that. Maybe not. So based on this naming, what is a transformation that would have mapped one of those onto the t'other? There's a couple ways to do it. I'm thinking this one. I'm thinking a 180-degree rotation. degree rotation. Wow, this is still like the best video I've ever done, though. I think we all agree. Yes, about the origin. There is another way I could transform those. I think if I reflected over the Y and then over the X, a double reflect, but we'll keep it at that. And if I did the double reflect, I probably would have called it oots. Oots, 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 oots. There you go. Remind Joshua to use that clip in any awesome sound. Yeah, awesome remix of Waddy Math. Oots, oots, oots. Man, that seriously needs to just be like the background, like bass line for any song that he does. Well, alternative naming convention here. So it turns out another name for a rigid motion or combination of rigid motions is called a congruence transformation, probably because of the obvious the preimage and image are congruent. And the terms rigid motion and congruence motion are transformation are interchangeable. There you go. Describe a congruence transformation that maps abacad onto ev. I don't know. I did not know this, no. Looks like a transformation by vector -5, 0 would bring me here. That's the way I'm thinking about it. So 1, translate by vector -5, 0. And then where do you think I'm going with this? You guys see it, right? How could I get from this guy to that guy? Yeah, reflect. Anyone have an alternative route? I think an alternative, you could have done this. Ugh, gross. All right, that's like vector, what, 0, -4? And that would have been here. And then reflect over y. There's a way I'm sure that could be done. Which way would that have been pointing? It would have been this to this. And then this here would have been over here. Yeah, you could do like a 180-degree rotation and then like a reflection over like this midpoint line. Or this line. Right? So yeah, so there's a bunch of ways you can do it. But yeah, I think it's helpful for us to think about that. Also, in terms of reading, here's a little bonus tip. Reading as parallelogram A, B, C, D. Yeah, so there's a little use of the parallelogram symbol. Guys, so we were in Geometer Sketchpad earlier, pre-video, and we discovered, or we conjecturified, this particular property right here. If lines K and M are parallel, then a reflection in line K followed by a reflection in line M is the same as a translation. Ooh. Yeah, we saw kind of like this result here. What? And so yeah, this triangle over here get mapped onto the double prime version. And that could have been a translation that did that. And we also determined that if that A double prime is perpendicular to K and M, so you can see these perpendicular symbols here and here. And then also we recognize this, that A to A prime, the macro distance, was twice the distance between those lines. And my argument was that this is congruent to that, and this is congruent to that. And if this was like X units and this was Y units, that this would have, the entire distance, D would have equaled X plus Y, and the entire would have been 2X plus 2Y. It's just double it, right? You done doubled it. All right. So, let's put that to use in ways that are somewhat pedestrian. Here we go. Example 3. Ooh. Reflections in parallel lines theorem. We could abbreviate the rippled. I don't know. I think so. In the diagram, blah. It says HB is equal to 9. HB is 9. And DH double prime is 4. It says name any segments congruent to each segment. Who is congruent to GH? Well, yeah, it's congruent to itself. So GH is going to be congruent to All right, you're going, yep. H double prime, G double prime. And that's also congruent to who? It's congruent. It's at a different like angle, but yeah, congruent, congruent, congruent. Because any reflection is a rigid transformation, and a double reflection will be a rigid transformation. Yeah. Mm-hmm. How about HB? Who's HB congruent to? H prime B is going to be congruent because this point and its image are going to be equidistant from the line it's reflected over. I could see trying to make an argument for this one as well, but I don't believe that has to be the case. Actually, let me using this sketch. Yeah, that doesn't have to be the case. Like, look, I can make these really close, but this segment is not changing in distance from its line. Okay. And then lastly, GA. G prime, G prime, right? Okay, there we go. And then they asked a question B, does AC equal BD? AC, is that equal to BD? Yes, those lines are parallel, right? We've got that label right here, and they are going to be, these are perpendicular to each other using the rippled, and perpendicular lines, yeah, they're these just, yeah. Those segments are perpendicular to the same line, and they're between two parallel lines, and the distance between parallel lines will always be the same. Blah, for all of that. Yeah, all right. And then what is the length of G double prime? So G to G double prime. Well, if this is 9, and then this is 9, if this is 4, then this is 4. 9 plus 9 is 18, plus 8 is 26, and I would argue that this distance also has to be 26. Because, yeah, I said so. Well, it's double reflection is the same as a translation, so if it translated H to H prime by 26 units, then G to G double prime is all. I said H prime instead of H double prime. Whatever. I think this just makes sense. And we didn't do this one, guys. But here's another theorem for you. It's a theorem. Oh, yeah. Oh, yeah. Not for this one. Not for this one. In chapter 10. Probably, maybe. Probably, maybe. So look at this. Here's a double reflection of non-parallel lines. Double reflection. And they say then the following thing is true. That the angle of rotation, all right, so double reflection of non-parallel lines is the same as a rotation, all right? That I could have rotated these or double reflected them, all right? And that the angle of rotation from A to A prime is 2x degrees, where x happens to be the angle of the intersecting lines. All right. Yeah, and I guess it does say to verify that or to clarify that, of the acute angle or right angle formed by those two lines. All right, so whatever the... So what you're going to have to do is just remember it's double and then remember which one the bigger or smaller one is what it'll be. So, ooh! Guys, look at this. This is like a little floppy fish. Like you caught a fish and then now it's on the shoreline and it's going flip-flop, flip-flop. Right? Yeah. F prime, F double prime. So juicy, sweet! It says the image is then reflected in line M after line K. Describe a single transformation that maps F to F prime. So I could have rotated about point P by what amount? Yeah, so because the acute angle between the lines was 70, all I do is I double it, and that's going to be 140 degree rotation, about the same point, and that it works out just like that. Just like that. Let's see. All right, where's this at? So, yeah, I think I'm good. Yeah, this was just kind of about, like, multiple ways that transformations can do the same thing. Have a good day, friends.